I'll take you through the question paper and also try to highlight on the possible responses and also try to give some brief explanations as to the justification of why we are opting for those options as the correct responses. Right. It is common to our understanding that our paper, one is made up of 3 questions. And out of those 3 questions, we're supposed to answer them in 3 hours, and they have a total of 150 marks. Implying that section A is a theory section, which is made up of 2 questions. Our first question is based on climate and weather, where we focus on the study of different weather phenomenon, ranging from the mid-latitude cyclones to urban climates. Then question number 2 is a geomorphology question, and our geomorphology focus in grade 12, we're mainly focused on the study of rivers. So that's the other question with 6 marks each, question number 160 and question number 260. Then we go to the section, next section B, which is question number 3. Question number 3 has got 30 marks and is based on geographical skills and techniques, which is basically our map interpretation. Right. So that's the structure of the paper, and you're supposed to answer everything in 3 hours. So I'll take you through the questions, starting from the first question, which is question on climate and weather, which is question number 1 in section A. Right. We see the illustration that we have there. We are having a situation of the Southern African subcontinent, and also we are having the coastal areas. And if we look at the 2 pressure cells indicated there, we have a high pressure cell, which is indicated over the interior here. This high pressure cell, we must be able to interpret before we answer the questions so that we have a clear understanding of what you are supposed to do and how we are supposed to respond correctly to the questions by mere interpretation of the sketch which is indicated there. So having a high pressure over the interior, we understand if we have a typical high pressure over the interior, this is our Kalahari high pressure cell. The Kalahari high pressure cell is the one that is dominant over the interior of the South African subcontinent. And if again we are supposed to interpret in another dimension, we can figure out the season here. We have our Kalahari high pressure cell dominating during typical winter season. Right. Then we are looking at the air circulation. We are seeing our circulation here is actually anti-clockwise, indicated by these arrows, which is typical of our southern hemisphere situation. When air is circulating out of a high pressure cell, it circulates in an anti-clockwise direction. Then we have the escarpment, meaning to say we are having now a difference in the altitude coming from the interior going towards the coastal areas. We have the escarpment here, we are going down to the coastal areas, and we see we have our pressure cell, which is indicated here. This pressure cell, if you are seeing its existence and its location, you are seeing that it's being located along the coastal region. The coastal region, we are saying the edges of land and water here. This is the edge of land and water. So automatically, if we were to interpret this pressure cell here, this is a coastal low pressure cell. We know that we have coastal low pressure cells, which tend to shift from the west going to the east, and they will dissipate around our Mozambican coast there. So having one such a cell here, it indicates that it's a coastal low pressure cell. And also its existence is coinciding with the presence of the Kalahari high pressure cell over the interior, which happens to exist in winter. And also the coastal low pressure, they are active during the winter season. So what we're supposed to interpret here is that given these 2 pressure cells, we have a high pressure cell over the interior and we have a low pressure cell over the coastal areas. We have typical pressure gradient force operating between those 2 areas, and that is going to force the movement of air from the interior to the coastal areas. And we understand because of the differences in the altitude of the 2 places, the interior is raised above 1,000 meters above sea level, whilst the coastal areas are just low, slightly above 0. So we know because of the differences in altitude, there is the process of adiabatic heating that is going to happen as the air descends from the Kalahari high going towards the coastal low. That is the basic understanding that we must interpret from this illustration here before we even attempt to answer the questions. Right, so going to the questions without wasting time, let's just try to figure out how best we can just answer the questions in as short as is possible. Right, taking us to the first question, the sketch shows dash conditions. We have answered that. That is typical winter conditions. We have the Kalahari high pressure cell dominating over the interior in the winter season. Right, the pressure cell at A is a dash low pressure cell. We have talked about that. That is a coastal low pressure cell. Let me tick here. Right, and the arrow at B on the sketch represents what kind of winds? The arrow at B, this arrow coming from high going towards the coastal area. What kind of wind is that? That is a backwind. Winds in question 113 above, it results in the shaded area being dash than normal. This area here, because of this wind coming from the interior, which is coming from the Kalahari going towards the coastal area, it results in this area here. How does it affect that particular area? The area becomes warmer. We understand that the backwinds are gusty, hot, and dry winds. They cause dry conditions. So they cause conditions warmer than normal conditions in that area, should it be? Then we have number 5, 115. The backwind conditions are usually associated with a dash pressure gradient. Right, what kind of pressure gradient? We have a high pressure cell dominating over the interior and a coastal low. So we have a steep gradient. That is why we end up having strong winds. We understand if there's steep pressure gradient, we tend to find the development of strong winds because of the nature of pressure gradient. If gradient is gentle, we have gentle winds. But in this instance, our backwinds, they are gusty winds, they are strong winds. Why? Because there's steep pressure gradient from the interior as they go towards the coastal areas. Right, then number 116, it says the weather conditions at question number 115 may result in the rapid dash or failed fires. Is it rapid spread or development? It's rapid spread. Because of the nature of the speed of the wind, it will ultimately also lead to fast spread of failed fires. Right, moving on to the next question. Backwind conditions are enhanced by dash adiabatic dash of air. That is adiabatic heating. Adiabatic heating as the air descends. Right, then the weather station model represents the weather conditions at B. Let's refer back to the weather conditions at B and see what it is like. At B, we're experiencing the formation of the backwinds here. So most likely because of adiabatic heating, the winds that go down the escarpment, if they happen to have any moisture, the moisture is going to evaporate because of adiabatic heating, which means there is no effective condensation that can take place in around area B. So which means it must give us clear conditions. And also in terms of temperature, we said the backwinds are hot and dry winds, which means you must expect high temperatures in the weather station reading. So going back to our weather stations, we can see the wind direction is basically the same. But if we check here, it's correct, the wind direction for both. But let's check the wind speed. This is 10, 15 knots. This is a gentle wind, but this one is 30. It means it's a gust wind. So we give credit to the wind speed. And also let's check the temperature. The coastal areas, the minimum is 1 and the maximum is 34, which is high. And also there is clear sky. There is no shade in the indication of cloud cover. So our correct response is Y. Right. That takes us to the end of the first part. We move on to the second part, which is question number 1.2. Question number 1.2 is based on a choice from the given two sets of words to make the statement correct. Number 121. The central part of a city, is it colder or warmer than the surrounding rural areas? Our correct response is warmer. Is warmer for the fact that we have what you call the urban heat islands. We have urban areas having higher temperatures compared to the surrounding rural areas or the surrounding farmlands. Right, that is an urban heat island, so the temperatures are warmer. They are warmer than the surrounding rural areas. Then the dash, is it transpiration or condensation process in vegetation that lowers temperature in rural areas? Right, it's transpiration, the loss of moisture through vegetation leaves, that moisture is going to have a cooling effect, right? So it's transpiration. Our wind speed is higher or lower in urban areas than in rural areas. What's the situation? Right, the wind speed is lower in our urban areas. Why? Because of the nature of the buildings that we have. The buildings, they block the free flow of the air, leading to lower wind speed. But however, in some areas, we might have channelized winds, which might be very fast. Like where there is a gap between some buildings, if wind is forced into that particular area, it can be having very high speed, what we call the channelized winds. But in general, we're saying in an urban area, because of the buildings, the density of the buildings, we tend to have a lower wind speed. Right. Then number 124, precipitation occurs more or less frequent in rural areas than in urban areas. How does precipitation compare between a rural area and an urban area? Precipitation is less frequent in rural areas. I'll try to explain. You might argue that why am I saying less? Why there is high chance of precipitation in rural areas? You can justify it that because there are more water bodies and maybe there's more vegetation contributing to transpiration. But the most important factor is not the presence of moisture in the atmosphere. But the most important thing towards the formation of precipitation is what we call the presence of the hygroscopic nuclei of condensation. We might have moisture in the atmosphere, but if there is no nuclei for condensation, that moisture cannot effectively condense to form precipitation. So why do urban areas have more rainfall chances than rural areas? It's because in urban areas, we have the presence of the nucleus, which comes in the form of dust particles, in the form of smoke particles. Those particles, they facilitate the condensation process. If there's any moisture in the atmosphere of an urban area, you tend to find that chances are very high of precipitation, of localized precipitation in the urban area compared to the rural areas. So it's less frequent in rural areas and more in urban areas. Right. Moving on to the next question, number 125. The temperature of a city can be lowered by painting concrete surfaces in dark or light colors. We know that dark colors are absorbent, while its light colors are reflective. So if you want to lower the temperature, we paint using light colors that reflect the heat and not use dark colors that absorb the heat. Right, we move on to the next part, which is number 126. Right, number 126 is an indication of a pollution dome. Right, when I'm looking at this situation here, I will try to illustrate the differences between a pollution dome during the day and a pollution dome during the night, so that we can answer those two questions in one explanation. Right, what I'll do here, I'll use my blackboard to explain the differences in the position of the pollution dome during a night situation and during a day situation. I will start during the day. During the day, what happens to the pollution dome? And do not also confuse the urban heat island with a pollution dome. When you're looking at a pollution dome, our focus is on the concentration of pollutants over an urban area. How concentrated are they over a particular urban area? That is a pollution dome. Right, so we are saying during the day, we understand, I'll give my illustration here of an urban area which is surrounded by a rural area. So we are saying this is rural, and also this is rural. And our urban is here. This is our built up area, which is surrounded by, we have our buildings, whatever buildings that we have. This is our built up area, our urban area, and this is the surrounding farmland. Right. During the day, we understand there are artificial surfaces over the urban area here. These artificial surfaces will absorb heat compared to the natural surfaces in the rural areas. So in terms of temperatures, we have high temperatures here over the urban area because of the absorbent surfaces. And in the rural area, temperature is relatively lower, and also temperature is lower here. And we want to relate the difference in temperature to the differences also that will exist in pressure cells that are likely to exist in those two different dimensions of temperatures. Right. If we check in the rural area where there's low temperature, it will also follow that the pressure will be higher compared to, we're now looking at pressure here, and also pressure here in the urban area will be lower. Because of high temperatures, the air is being uplifted. There is less concentration of air molecules. And here in the rural area, the pressure is higher. So we are seeing that there's pressure gradient between the rural area and the urban area. And because of that instance, that results in the feeding in of air into the urban area. Air feeds from the rural area into the urban area, and also from the rural dimension of other side into the urban area. These two air masses are going to converge, and as they converge, they're going to uplift over the urban area. As they uplift, they're going to diverge in the upper atmosphere. Right, as this process happens, this air which is converging in the urban area is also going to lift pollutants. There are pollutants here from industries, from smoke from vehicles, dust particles. They're going to be lifted into the upper atmosphere because of the convection currents. And as a result, the shape of our pollution dome becomes a mushroom shape during the day. This is the shape of the pollution dome. Pollutants are up in the atmosphere. They will be lifted by convection currents, which will be taking place during the day. So during the day, there's less concentration over the urban area. Remember, people are just here. They are not very much affected because the pollutants are up in the atmosphere. They've been lifted by the convection currents. That is the day situation. Let's look at the night situation. Right, at night, we are saying the pressure gradient is no longer working because the sun has set. We no longer have higher temperatures in the rural area and no longer have lower temperatures wherever. The temperatures are now just almost the same because the sun is no longer heating the surfaces. We now have long wave radiation. And typical of this urban heat, of this pollution dome, they are most felt during the winter season. People in urban areas, they are mostly affected by the presence of the pollution dome during the winter season. Right. So during the night, what is going to happen is we still have our urban area here, our tall buildings, we still have them. But what is happening is the pollutants that have been lifted during the day, now they are being suppressed. They are being pushed down. Who is pushing them? We are talking of a winter season here. We know that during the winter season, we have the dominance of the Kalahari high pressure cell, which is constituted by descending air or sinking air. So the sinking air here, during the day, because there's intense heating, the high pressure cell is weaker and is elevated, what we call vertical displacement. It is displaced vertically because of the heat that is being received by the Earth's surface during the heating times of the day. There is insolation, which results in the weakening of the high pressure cell, and it vertically displaces itself to the upper atmosphere. But at night now, it's being forced to go down because there's no more heat on the Earth's surface, and now it's night situation. The dense cold air is now pushing down the pollutants. So you tend to find that during the night, it takes this shape here, not the day shape, because the pollutants are being pushed down by the strong descending air from the Kalahari high pressure cell. As a result, the pollutants are now concentrated. We now have the pollutants concentrated in the urban area. During the day, they were high up in the atmosphere, but at night, they are lowered because of the lowering of the pollutants by the strong descending air from the Kalahari high pressure cell. So this is the night situation, comparing the two, the pollution dome during the day and the pollution dome at night. That's the situation. Let's go and answer the questions. Right, so this sketch here, we do not waste time. This is a night situation. We've discussed about that. We have seen the shape of the pollution dome. Then the height of the pollution dome indicates the presence of a dash convectional currents over the urban area. There is less convection currents. If there are more convection currents, it will have a mushroom shape and the pollutants will be lifted in the upper atmosphere. Right, that takes us to the end of question number 1.2. We move on to question number 1.3. This question is based on mid-latitude cyclones, and some of the information we are going to extract it for the answering of the low order questions, and also we have a satellite image that you need to interpret and also be able to relate to the text information to be able to answer the questions. Then we also have a cross section through a mature stage of a mid-latitude cyclone. Right. Provide the reason from the article for the record rainfall experienced around Cape Town. What is the reason from the article for the record rainfall which was experienced? What caused the record rainfall? That's the question. If you come to our source here, to our infographic, our answer, we find it here. It is saying South African city of Cape Town and surrounding areas were hit by more storms on Thursday that ripped off houses and causes widespread flooding, forcing at least 4,500 people out of their homes and damaging at least 15,000 structures, authorities said. The devastating weather began a week ago. Multiple cold fronts have battered the region on the southwest of the tip of Southern Africa late since last week, bringing a record rainfall. So what caused the record of the record rainfall is multiple cold fronts. We know that the coming of the cold front is the one that brings in heavy rainfall that poses the risk of flooding over the Western Cape region during our winter season. So multiple cold fronts. The next question is saying, identify the type of cloud indicated at Y. Right. We are looking at on the satellite image. Right. If we check, we have this nature of cloud here. This is the side of the cold front. You can see that tall cloud on the side of the cold front, and you have this moderate cloud here on the side of Y. This, what you are seeing here, is what is here, and this, what you are seeing here, is what is here. So, what kind of clouds happen to exist on the side of the warm front? In simple terms, we have on that side, we have the stratus. Those are typical clouds that we find. We have the stratus clouds, the nimbus stratus to be specific. Those clouds that produce a moderate amount of rainfall, but which is long-lasting. They produce torrential rainfall, long-lasting rainfall, because those clouds, they form gradually because of the nature of the gradient of the warm front. Condensation takes place gradually, while the warm front also moves gradually away from the cold front. So the nature of rainfall that we experience on that side of the warm front is long-lasting rainfall from the nimbus stratus clouds. They are stratus clouds on that side. Then account for the development of the cloud type at Y. Why do those clouds develop? Like what I've been indicating. What makes the clouds differ in terms of their development? If you look at the cold front side and the warm front side, we are saying we have cold air on this side. I'll just try to make an illustration. And then we have a cold front. Then we have a warm front on this side. Right. So for this reason, we are saying our movement direction of this weather system is in that direction, going from the west going to the east, or in the easterly direction. So for this reason, we are saying there is warm air on this sector here. I think I'll also be answering the other questions to come using this illustration, because there's a question which requires you to do some other illustrations there. Right. So we are saying there's warm air in this area here, which is the warm sector. And then there's cold air from behind, and also there's cold air from the other side. So if this system is moving this direction, it's circulating and it's reducing the warm sector area here. By reducing the warm sector area, we are saying this is the area that is featured by warm and moist air. Warm and moist air is contained between two bodies of cold air, but the nature of the gradient between the two cold air bodies is that on the left side or the western side, the cold air is advancing faster, and hence it has a steeper gradient. It's pushing faster towards warm air, while its warm air pushes gradually towards cold air on the warm front. This is our cold front on this side, and this is our warm front on this other side. So for that reason, we have a general gradient here. This front has got a general gradient, and this front has got a steep gradient. So air which is being forced here, remember air is being displaced from the ground surface. This space is shortening up, is being finished from the ground surface, and all the air is being forced to uplift to reach condensation level and to create clouds that are going to produce rainfall, because the clouds are warm and moist. The air is warm and moist. So for this reason, because the steepness here is just a steep gradient, the air is also going to be forced to rise vertically, with what we call the vertical updrafts. And the nature of the clouds that are going to form here, we have towering clouds because of the nature of upliftment which is happening on this side. That is why we have the cumulonimbus clouds. But clouds that form on this side, they are not as forced to vertically uplift as what is happening on this side. These ones, the air is forced to rise gradually along the warm front. It rises gradually, condensing gradually, and creating rainfall, which is lasting. This is where we have our nimbus stratus on this side. So when you are explaining, you explain based on the nature of the gradient of the front over which the clouds form. These clouds, they form over a general gradient, and as a result, condensation takes place moderately, and the clouds tend to produce prolonged rainfall because of the nature of the upliftment which is happening there. But here, it's very heavy rainfall, but which is short-lived. It's short-lived because the cold front is advancing, it's moving. This cloud would ultimately lose all the moisture because it has been forced to uplift vertically, and the moisture is going to be lost, and the rainfall is going to cease as the cold front keeps on pushing towards the direction of the warm front. Right. That is how you're supposed to describe that one in your own words. Right. Then moving on to the next question. The next question is saying 134, state the general direction of movement of mid-latitude cyclones. You can use two descriptions of direction. You can say they move from west to east. That's the movement direction. Or you can say they move eastwards. It's one and the same thing. Moving eastwards, it means you're going to the east. Moving from west to east, again, you're going to the east. So that's the movement direction. Give a reason for the answer to question 1, 3, 4. Right, this is grade 11. I might not need to waste time. I'll just give you the response. They move from west to east under the influence of, they are influenced by the westerlies. They move from west to east under the influence of the westerly winds. The westerly winds are the ones that drive them to move from west going to east. So they are influenced by the westerly winds. They move from west to east under the influence of westerlies or the westerly winds. Right. 136, explain how the general direction of movement of mid-latitude cyclone in the above answer resulted in the flooding referred to in the article. We want to relate movement direction to flooding. How does the movement direction result in flooding of the areas indicated in the infographic? Right, what you must explain here, you must explain the cold front position against the warm front position, like what we have been indicating here. Right, I'll use this illustration here, like what I was saying. Right, we are saying this weather system, it moves from west. This is our western side, and is going to the eastern side. We are saying, how does this movement direction result in flooding? So we are seeing that this weather system, the cold front, the cold air is pushing warm air towards the eastern direction. This weather system originates over the cold oceans there, over the Atlantic Ocean, and it pushes towards the Western Cape. as it moves from west to east. So for this reason, we are saying the weather system is having a cold front on the extreme western side, pushing warm air towards the eastern side. You understand? We are saying our Western Cape region is here. How is it going to be affected by flooding? Atlantic Ocean is here. This weather system is starting over the Atlantic Ocean and is moving towards the Western Cape region of South Africa. It's pushing warm air towards this region. But however, the warm air now, because of the presence of this stronger cold front, it is going to forcibly uplift the warm air. And this warm air, which is being uplifted as the weather system goes to the east, is the one that is going to cause heavy rainfall. And the heavy rainfall is the one that is going to cause flooding over the Western Cape region. So you relate to the weather system to the movement direction, and apparently how it leads to the formation of rainfall on the eastern side. Because remember, our rainfall is realized ahead of the cold front. You understand? It's ahead. We don't have rainfall here. Once the cold front moves, there's no more rainfall. So rainfall is realized ahead of the cold front. That is why it is going to affect the Western Cape region here, because the Western Cape is ahead of the cold front. The cold front advances towards the Western Cape in the eastern direction. And as it advances, the cold front is forcing the warm and moist air to uplift. And that warm and moist air, as it's being forced to uplift by the cold front, is going to condense and is going to cause heavy rainfall that is going to cause flooding over the Western Cape. That is how you relate the two. Right. We'll move on to the next question. Draw a labeled plan view of the cross-section from A to B. The following must be shown in the drawing. Right, this what we have here is what we call a cross-section. If you drew this diagram, it's wrong. This is a cross-section. A cross-section is a side view. If you are to look at this weather system, when you're looking at it from a side, what are you going to see? This is what you're going to see. The question here wants a plan view or an aerial view. A plan is an aerial view. Aerial. You understand aerial photographs. They are taken from above. If you were to look at the weather system from above, how was it going to appear? That is what the question is asking. So you must not use the cross-section view. You must use the plan view. Our plan view for the weather system, you're supposed to draw something like this. This is your cold front, and our weather system has reached maturity, which means our home sector is narrowed. You draw that, and then you draw your isobars going right round. You put the other isobar going right round, like this. Right. Something like this. These are isobars. So you're supposed to indicate, when you're drawing a plan view, remember, use these symbols for the indication of the cold front and the warm front. Our cold front use these triangular symbols to indicate that it's a cold front. Then for the warm front, you use this more of semicircular. This. Right. So you're supposed to indicate what? Position of the cold front. This is our cold front. And this is our warm front. And then the cold air, we find it here. And the cold air will be warm air in that direction. That's basically what you're supposed to illustrate. And then maybe you can put it in a frame. But that doesn't matter. But what is important is you're supposed to indicate something like that to show your home front and your cold front and the section with cold air. So it means this is our home sector, which is narrowed because our weather system has reached a maturity. Our home sector is narrowed in that instance there. That is what you're supposed to draw for that particular question to get your 4 marks. Right, move on to the next question, number 1.4. Number 1.4 is talking about a tropical cyclone Dikeledi. Right, we're not going to go through the text. We are going to just extract information and answer the questions. Right, we are seeing a situation here. How many tropical cyclones have occurred before tropical cyclone Dikeledi? I think that is a common understanding. When you are looking at our tropical cyclones, we understand geographically our tropical cyclones, they are named alphabetically. What are we saying here? They are named according to the letters of the alphabet. We have A, B, C, D, E, F. In every particular season, we name our tropical cyclones according to the letters of the alphabet. Maybe the first tropical cyclone to happen in a particular season is named Alpha. Maybe the second one is called Beauty. Maybe the third one is called Caroline. Maybe the fourth one is called Daphne. Maybe this one is called Elizabeth. And lastly, maybe it's called Faith. That is how we name our tropical cyclones. They are named according to the letters of the alphabet. So the question is saying, how many tropical cyclones have occurred before? Take note of the term before cyclone Dikeledi. So going back to our alphabet, D is letter 4, which means prior to this, we had 3 cyclones. Before this, we had 3 cyclones that we experienced. Letter A, B, C. Then we had letter D. So the question is saying before, which means you must not include that one. Provide the reason for the answer. The reason is there. We are naming our tropical cyclones according to alphabets. And letter D is the 4th alphabet. Therefore, 3 have occurred. Right. Refer to the map extracts and determine the air pressure at the center of the tropical cyclone. Right, we want to refer to the map extract. Right, we want to analyze the effect of reading our pressure readings on the synoptic map. Right, if we check, we have a high pressure here, which is having 1020. And let's ignore this. Let's move on to our side of the interest here. We have 1016. And 1016 here, we are approaching towards a low pressure, which means our pressure readings must decrease as we go towards the low pressure and must further decrease as we reach the center of the low. So if this is 1016 and there is an unnumbered isobar between, and we have 1008, it means our interval here, if we read this 1008 to 1016, we have a gap of 8 between 1008 to 1016. We have a gap of 8 hectopascals. So the implication is if there is an isobar between the two, it must also be half of the difference between the two, which means it must be 4 less than this. So this is 1016. So it means this one must be less 4. 16 less 4 gives us 1012. Then 1008. And then we are going towards the center of the law. This must be an interval. This, before we reach the center, we must also subtract an interval of 4 from 1008 to give us 1000. Sorry, 1004. Right. So it means as we go towards the center of the system, as we approach the focal point of our weather system, our pressure must keep on decreasing, must keep on going down. So it must be below 1004 at the center of the system. It must be according to the readings that we have been following there. Explain why tropical cyclone Dikeledi weaken when moving over land. Why do tropical cyclones lose their intensity as they approach land, as they move from water bodies to land? I'll just indicate 2 reasons here. One is because of frictional drag. Water, remember, when they're moving over the oceans and the seas, there is less friction because it's a smooth surface. But as they approach land, they are going to face rough surfaces that are going to reduce their speed, and they are going to weaken. And also we know they also need to be fired by latent heat of condensation, which is released during a condensation process. So over land, there is also less moisture to facilitate the release of latent heat through condensation. So they will also lose their intensity because there are less water bodies over land. There is less presence of moisture over land compared to water. Then number 145, it says in a paragraph of approximately 8 lines, discuss how strong winds and heavy rain will impact negatively on the natural environment. This is a specific question. We want to look at the natural environment. How do strong winds, our focus is on strong winds and heavy rainfall. So your discussion must focus on the two. You must not focus on one. You must focus and balance your discussion by looking at the two weather phenomenon. Strong winds, how do they affect? We can look at strong winds uprooting trees and destroying vegetation. They are impacting on the natural environment. If they uproot trees and destroy vegetation, then that is a negative implication. Or we can also look at strong winds having a negative impact on destroying natural habitat. The habitat is destroyed because of the strong winds. As they destroy vegetation, as they destroy the natural environment, we also lose the natural habitat. Then we can also look at heavy rainfall. It can result in flooding, which is a negative implication on the environment, natural environment. Flooding damages a lot of things and disrupts ecosystems. We can also talk of disruption of ecosystems. It's a natural. The balance of nature is disturbed by heavy rainfall. We can also look at other things like increased soil erosion. Soil erosion increases because of heavy rainfall. There is heavy runoff, which facilitates the removal of topsoil, which affects the natural environment. We also can look at other impacts like the risk of mass movement processes like landslides can also be facilitated, or rockfalls. Either strong winds and heavy rainfall, they can cause landslides or mudslides or rockfalls. Those are some of the negative implications. Your focus must be on the natural environment, not on the economy or not on social life of people, but focus on the natural environment. Right, that was our last part of the question number 1.4. We need to move on to the next question. Number 1.5 is an infographic talking about valley climatic situations. Talks about katabatic wind, installation in the valley, and also a photograph of a valley. Right, define the term slope aspect. Right, when I'm looking at slope aspect, this is a geographical term which we use to looking at slope aspect. I'll describe it in simple terms so that you can figure out a simple definition. We are saying slope aspect refers to the direction faced by a slope. What is the direction that is faced by a slope? That is slope aspect. For example, if this is our south and this is our north, and we have a valley, this slope is north facing. That's the slope aspect. It's facing towards the north. And this one is south facing. That's the aspect of the slope. So that's basically a slope aspect. Right, moving on to the next question, we will look at the other things. Provide evidence from the insolation of the valley sketch that the valley is located in the southern hemisphere. What justification can we give from that illustration of insolation in the valley to show that this slope is in the southern hemisphere? Right, we use justification of these arrows here. These arrows are indicating insolation, you can see here. So why is it in the southern hemisphere? This is a south slope. Let me do the illustration maybe to make it clear so that we don't confuse the two concepts. Based on most of the learners, they get confused. Right, we are saying our situation is like this. Our insolation is showing that it's facing this direction. And this is written south. And this is written north. So what justification can we give to show that this slope is in the southern hemisphere? In the southern hemisphere, southern slopes receive insolation. We are looking at a winter situation here. In winter, south slope receive insolation. Why? They face towards the sun. Remember, during winter, the sun is lower in the atmosphere. It cannot reach some part of the slope. And northern slopes, they are in the shadow zone. They face away from the sun. That is in the southern hemisphere. Northern slopes, they are in the shadow zone. They face away from the sun. Southern slopes, they receive insolation. They are facing towards the sun. Right. So this one, we call them, they are in the zone of incidence. This is in the shadow zone, and these ones, they are in the zone of incidence. Right. And the confusion that you must desist from, if ever you don't want to have confusion in your life in the examination. Remember, south slopes, we also call them north facing. It's one and the same thing. A slope which is in the south is facing to the north. A slope which is in the north is south facing. So you must not confuse those two. A north facing slope in the southern hemisphere is a southern slope. A south facing slope in the southern hemisphere is a northern slope. I think that is clear. Right, let's move on. Account for at which slope C or D will be the shadow zone in the photograph developed. C or D, our shadow zone develops where there is a limited insolation. So it will develop a D. You can see there that is dark at D and is lit at C. The northern slope is the one which is in the shadow zone. Account for the difference in vegetation between slopes C and D, which is evident in the photograph. If you see the vegetation here, you can see we have thick vegetation here. And here we have just sparse vegetation. Account for the difference. What constitutes the difference is there. The northern slope is having thick vegetation, is having those tall trees, while it's the south facing at sea is having some sparse vegetation. So this side here, basically when I'm looking at vegetation, the shadow zone, it supports forestry. It supports forestry. Meaning to say, trees that require shade and more moisture. Remember, there will be high moisture retention there. They are the ones that grow well on the side of the shadow zone. So for that reason, that is why we're having dense forests. Forestry trees, they require shade and also they require high amounts of moisture. They do well in the shadow zone. While if you're looking at this side here, the at C, it mainly supports fruit trees that require sunlight. And those trees are not as dense as the forestry trees. If you compare fruit trees like the citrus fruits, they don't give us that density of vegetation. So the difference will account for the nature of vegetation supported by the two sides. The shadow zone supports forestry. It requires, it does well for the crop, for the trees that require high amounts of moisture and that do not require sunlight. While it's at sea, we can only effectively deal with crops with vegetation that requires high amounts of sunlight and limited moisture. That is why we have sparse vegetation on that side and we have denser on the other side. Right, refer to the extract on the katabatic winds in a valley. Explain how katabatic winds can lead to the development of a valley inversion. Right, I'll try to illustrate clearly here on my whiteboard. Right, katabatic winds, how do they result in a valley inversion? Right, we must understand what an inversion is. An inversion, basically, when we're defining it geographically, we are saying it's the reversal of the normal temperature profile in the troposphere here. We are referring to our zone of the troposphere. Our temperature profile must be, we must have a negative temperature profile. The higher we go, it must get cooler. But if it reverses that we are going up and it's getting warm, then it's an inversion. Or in simple terms, we are saying it's an increase in temperature with increasing height. If temperature is increasing with an increase in height, then it's an inversion. So how does it happen? Because of the presence of katabatic winds in a valley. I will use an illustration and you will figure out explanation from the illustration. Right, this is a valley. Right, katabatic winds, we said they are night winds. They are night winds. How do they happen? The valley sides, they cool excessively. The valley sides, they become very cold at night compared to the floor here. The floor is warmer. The valley floor is warmer than the valley sides. The valley sides are very cold. They have lost heat due to long wave radiation. At night, there is terrestrial radiation, which is resulting in the loss of heat on the valley sides. As a result, the air which accumulates here, it is cooled and it becomes heavy. As it becomes heavy, it sinks. We cannot have cold air sustaining there. It's cold and heavy, it tends to sink. As it sinks into the valley, what is it going to do to the warm air which was already in the valley here? This warm air is less dense. It's going to be forced to rise. And the warm air is going to fall above cold air. So this whole part here, because of katabatic, is going to become cold. And the upper part of the valley is going to become warm because of the displacement of warm air. It's going to be displaced. So as a result, if you look at our profile here, coming from the valley floor, going upwards, from the valley floor, it's cold. But as we go up, it is getting warm. This is an inversion situation. That's basically how you explain that using an illustration. But you're supposed to explain using text. Right. That takes us to the end of our question number 1, which is a question on climate and weather. We move on to our second question, which is a geomorphology question. The first question is based on the 2 types of river flow, river discharge flow. We have what we call the laminar flow and the turbulent. Laminar, that is a steady flow where water flows over an even river bed. And there is no turbulence. The river flows in parallel sheets. While it's in turbulence, we are saying the river bed is uneven. Water flows and upwells and creates the white water situation because of the unevenness of the river bed. All right, let's go and answer the questions. The first part is saying the flow pattern in which water flows in parallel layers occurs in dash diagram. Parallel layers, they occur in A, where there is lamina. The diagram A or B represents a flow pattern that occurs in the upper course of the river. That is automatically B. We tend to find that in the upper course, that is where we have typical landforms of erosion like rapids, where the water flows in that manner. Right, obstacles in the river channel have resulted in the flow pattern in A or B. Obstacles, they result in turbulence. As the water flows over obstacles, it tends to turbulate. Right, diagram A or B shows the flow pattern that occurs over an even and gently sloping, that is A. In diagram A or B, the flow pattern results in a higher rate of erosion. Erosion is facilitated by B. The flow pattern that mostly occur on an ungraded river profile, ungraded is B. Formation of oxbow lakes is most likely to occur at A. Right, that is the first part. Move on to the next question. River rejuvenation. When we're talking of rejuvenation, we are saying it's the renewal of erosive power of a river. The river regains its erosive power. That is rejuvenation. A river regains its erosive power. So the correct response then is item B. The number 2.22, river rejuvenation is likely caused by what is likely to cause river rejuvenation? For a river to renew its erosive power, deposition is irrelevant, rising of sea level is irrelevant, rising of land along the coast, yes. If there's what we call tectonic uplift, the river is now flowing over a steeper gradient and then it regains its energy to erode downwardly because of tectonic uplift. Right, A or N is a feature commonly associated with river rejuvenation. What do we find when we have river rejuvenation? Floodplain is a result of deposition. Incised meander is our correct response. Or sometimes we call them entrenched meanders. They happen because of river rejuvenation. And also other landforms like terraces, they are also a result of river rejuvenation. The valley in valleys, there are also other features. A delta is a feature of deposition. A levee is also a feature of deposition. It's irrelevant, right? So our correct response is incised meander. Rejuvenation, rejuvenated rivers will have a dash energy level resulting in increased dash. High or lower energy, automatically the energy is going to be higher. They are regaining their energy to erode and also resulting in increased erosion. You cannot have high energy with high deposition. Right, so our correct response there is item B, which matches 2 and 4. Right, move on to the next question. A river capture is when a river on a dash altitude intercepts the waters of another river through a constant dash erosion. We understand a river which is more energetic is a river which is flowing on a lower altitude, which is advancing towards the watershed to reach another river at a higher level. And what makes the river able to reach that area is because of headward erosion. Headward erosion, we understand, is that type of erosion which is responsible for lengthening the river channel. The river becomes longer and longer because of headward erosion, whilst lateral is responsible for widening. We also call this sideway erosion. Right, so our item number 2 and item number 3 at letter B, so correct response. Right, on to the next question. 226, wind gap, confluence, source of the river, elbow of capture. The feature formed at the location where the captured stream is diverted into the capture stream. Right, let me just make a quick illustration here of the river capture process. Right, when you are looking at river capture process, let's assume you are having our 2 rivers. This is our watershed, and this is our low-lying area, and this is our high-lying area. Right, we are saying our areas are like this. This area is low-lying, and this is our watershed. So we have a river flowing of a low-lying area here. It has its tributary advancing the watershed like this. This is, let's say, a river B is going that direction. And we have river A, which is also flowing over this area, A, with also its tributaries somewhere. Right. So what happens with this process? We are saying this river here is the one which is more energetic, is the one which is getting more energy, and which one which is advancing, the one which is flowing on a lower ground. This is on a higher ground. So what is going to happen is this tributary here, we're focusing on this. Because of headward erosion, it is going to continue lengthening its channel, lengthening its channel, lengthening its channel until it gets here. Then this was the source of supply of water for this stream. So we are saying in this instance, capturing is happening at this particular point, meaning to say all the headwaters coming from this side, they are going to be diverted towards this side here because this stream has managed to cut through the watershed by headward erosion. And there is likely to be deposition in this area. Right. This area becomes what we call the wind gap, this area which is filled with deposits. And this stream that is going to continue is the one that we are going to call the misfit stream. And this one which has been taken is the Cape Shad stream. And this one which has managed to take intercept is the Capta stream. And then we have this bend here where capture has taken place. This is what we call the elbow of capture. So basically we are saying that's the process of river capture. We're going to have high discharge here because of this water coming from this part, which has been intercepted by this stream, benefiting mainstream B because it has managed to cut through the watershed to intercept waters from stream A. So our question is referring to the elbow of capture here, where water is diverted. The question is saying a feature formed at the location where the captured stream is diverted into the captor is known as the elbow of capture. Right. River capture is caused by what causes river capture? Headward erosion by a more powerful stream. Don't want to waste time. Right. A misfit stream can be described as what kind of stream is a misfit? According to what we have explained there, the stream originally was flowing into a bigger in a bigger valley because it was having high discharge. But however, because its headwaters has been intercepted, it's now a smaller stream. So the situation is now it's a small stream which is flowing in a valley which is disproportionate to its size. Right. Too small for the valley in which it flows. That's the correct response. Right. We move on to longitudinal river profiles. We have river A with rapids and river B with a smooth concave shape. That is an ungraded profile on A, and in B it's a graded river profile. Right. Let's tackle the questions. Define the concept ungraded profile. When you're looking at river profiles, and a profile is ungraded, an ungraded profile, we are saying there is no balance. Is a stream or a river in which there is no balance between erosion and deposition. Or in simple terms, we can say either in that stream, one of the two, it can be erosion or deposition dominates, but not both of them. They are not the same. One is dominating the other. That gives us an ungraded river profile. It's a river profile in which either deposition or erosion dominates, or there is no balance. And that results in the existence of what we call the temporary base levels of erosion. They result because of the imbalance between the two river processes of erosion and deposition. If they are not equated to each other, then the river becomes ungraded, and also will experience a situation whereby the river will have some temporary base levels of erosion along its channel. Right, going on to the next question, does river A have a graded or an ungraded? A is ungraded. We have mentioned that. Right, provide evidence from the diagram to support the answer. It's ungraded because it has rapids, which are temporary base levels. The presence of rapids, this giving us some nick points. We have rapids which are giving us nick points along the channel. It's ungraded. We don't have a smooth concave shape. So it's ungraded. It implies that there is no balance. Presence of rapids indicate that there's no balance between erosion and deposition. So these rapids are clear evidence that there is no balance between the process of erosion and deposition. Right, number 234, it says, in the longitudinal profile of river A, identify the permanent base level of erosion. Permanent here is our sea level. The sea, the level of the sea here is the permanent. If the river starts to erode from the level of the sea, going up until its source, it is going to achieve a grade, like what is indicated by this dotted line here. If this river starts to erode from this level, it is going to reach this particular point, creating smooth concave shape indicated by the dotted line or the broken line here. So this is permanent, the sea level of the sea. And then the temporary, these rapids here, they are temporary base levels. The rapids are temporary, or the nick points. We have these rapids creating sharp gradients, which are nick points. Those are temporary base levels of erosion. Describe the shape of the longitudinal profile of river B. Longitudinal profile of river B, you can see it's a smooth concave from the source to the mouth. Starting from where the river is starting, it maintains a smooth shape, which is concave, until where it ends. That is how we can describe that. Right. Explain how erosion and deposition contribute to the shape of the longitudinal profile of river B as described. How does erosion and deposition in combined effort lead to achievement of a grade? Right. What you're saying here is, I will try to make an illustration to get the sense. If a river is ungraded, I'll use the illustration to explain. You get the explanation from there. Right, let's say that's the source, and maybe there's a waterfall, maybe there's a dam, and maybe there is a lake, and maybe whatever other feature which contributes towards an ungraded. Maybe we have rapids somewhere up here, then we have a waterfall here. Right. Let's assume this is our longitudinal profile of the river. Our sea is here. For this river to achieve grade, it needs to start from the level of the sea here until it gets to its source. For it to maintain a smooth concave shape, there must be erosion taking place and deposition taking place for this river to maintain and have a smooth concave shape. So the implication is erosion is going to affect these nick points. For example, the waterfall is going to be affected by headward erosion and is going to have the cape rock falling away and ultimately being worn away. We are seeing this waterfall here is being eroded. These rapids are also going to be eroded. Where is this material going to go? This is now eroded material. which can be broken down into sediment. Where is it going to go? It must come and fill here. This material here, eroded from here, must come and fill here. And also this must be transported and must come and fill this. And ultimately, if the river also starts to erode from here, it must maintain a smooth concave shape because these areas are filled up. These areas are already filled up, meaning to say the river will end up achieving a smooth concave shape from its origin until it gets to where it ends. So what you explain there, you explain the effect of erosion. Erosion is going to affect some temporary base levels of erosion by eroding the nick points. Nick points like waterfalls and rapids will be eroded and they will migrate up the stream. We understand if there's a waterfall, if the Cape Rock falls, the waterfall is going to migrate upstream until it gets finished. So the material which comes from the eroded part of the nick points is going to fill this. If there are lakes along the river or if there are some dams along the river, these are temporary. They're going to be filled by material which is being transported, which is coming from the eroded nick caps. And as a result, low-lying areas will be filled up and sharp, steep areas are going to be eroded into smooth concave areas. At the end, we are going to have a smooth concave shape, which results in equilibrium between erosion and deposition. Once you achieve equilibrium, then it means we have a smooth concave shape from the start of the river to where it ends. That's the argument that you're supposed to use there. Though I've used the diagram, but that is what you must describe when you want to explain how the river achieves a grade from being ungraded. Right, then we move on to the next question. Our next question is based on refer the diagram on natural levees below to answer the question that follow. Right, these are our natural levees, and we have our river there, and the floodplain adjacent. It is made up of sediment of layers of sediment. What is a natural levee? That is our question. Right, when we are describing our natural levees, we can describe them in simple understanding as they are raised river banks made up of sediment. Or we can say they are embankments. Meaning to say the normal river bank has been uplifted, has been raised because of deposited material. And what forms the natural levees? They form as a result of successive phases of flooding. If there's flooding, water overflows the river channel and it deposits some material along the banks of the river. That sediment deposited now will accumulate and create a raised bank. That raised bank or an embankment is what we refer to as the natural levees. Right, then the question is saying in which course of the river is the floodplain in the diagram most likely to occur? Much of the floodplains, we find them in the lower course where the river gradient is now gentle. The river is flowing over a gently sloping area. That is where we most find our floodplains. What type of erosion is dominant in the river shown in the diagram? Type of erosion, right? Type of erosion we say is lateral erosion or it's sideways. That is what is most dominant there. Then I use the evidence on the diagram to explain how flooding leads to formation of natural levees. Like what I've been saying, we are saying during a flood, the river deposits material. Deposits material on the banks of the river. And this material accumulates. Remember, we do not have one flooding session. We have successive flooding sessions. If there are repeated flooding sessions, more material is going to repeatedly more material accumulates. Resulting in raised banks of the river. The river becomes starts to have an embankment along the channel because of successive phases of flooding. And also what you must note is there is a coarse material and also a finer material like silt. The coarser material, which is heavier, is the one which is deposited just close to the river channel, adjacent to the river channel, just close where it deposits heavier material, and lighter material gets to be displaced further away from the river channel. So that is basically how the flooding relates. So if you are seeing here, it says layers of sediment. How do those layers come into existence? It's because of repeated sessions. If flooding repeats, if there's flooding at this particular time, it leaves a layer of sediment. Then it floods again, another layer of sediment accumulates. If it floods again, creating these embankments here. That is why we are saying we have different layers. This is the first layer, another layer is deposited again in the next flooding session. Another flooding session brings another layer again until we have the raised banks of the river channel. That is basically how the natural levees form. Right, draw a labeled cross-section of the river from A to B. The cross-section must show the shape of the river valley and the position of the natural levees. This is just a simple question. If we check the shape here, the river channel is straight and it has a regular shape. And we want to look at the position of the levees, how we're going to position them. So in simple drawing, we must just draw a river channel like this. Right, we are saying our A, let's say A is there, and our B is here. We want to draw a cross-section. That is our river channel. That is our river channel. Right, our A is there, our B is there. Our river channel is there. Our water level is there. Now we want to illustrate our position of the levees. Let me just put my letters somewhere a little bit further so that we can have. Then we are saying our natural levees are going to form here. And they are going to have that shape there. And another one is going to form here. And it's also going to have that shape there. And remember, they are made up of some different sediments, which means they are made up of different layers, which were deposited by different phases of flooding. And also what you must, so this our natural levees, one on one side, the another one on the other side of the river. That's our river channel, and those are our raised embankments. So the implication is the original level of the river bank is this, but now it has been raised by the accumulated deposits. And also here, the original level is this one, and then it has been raised by the accumulated sediments, giving us the natural levees. Our shape of the river channel must resemble something, the regular shape like this. So basically, that is what you're supposed to illustrate there. Right, let's move on to the next question. Our next question is based on evaluate why site X would be suitable or good location for the development of a rural settlement. We are looking at site X here. It's on the floodplain. Why is it good for the development of a rural settlement? Rural settlements, we know that they are unifunctional, they rely on agriculture. So being it on a floodplain, we have fertile deposits which can support crop production. We can have successful crop production there because of fertile deposits which has been deposited by floods around area X. So it's a benefit that rural settlements can have successful farming activities. It's good for farming because the soils are rich in nutrients. Then you can also talk of access to water. It's easy to access water for the different purposes, for livestock and for irrigation purposes. The river is just adjacent and the river channel is not deep, such that it's easier to extract water for the different purposes. And also, There's flatland. Flatland, which is easy to work on. Rural people, when they're doing the activities, they need to work on areas which are easy. So it's easy to work on, and also it's cheaper to do construction because the area is flat. Cheaper to construct, and also it's also cheaper to develop infrastructure in that area. You can easily develop infrastructure in that particular area. And then also maybe we can talk of other resources, like it can be fish resources available. You can have a fishing village there developing because the river is just nearby and it's very easily accessible. Then you might have development of fishing villages around those areas. Right. That was that particular question. Moving on to the next question. Refer to the extract below on river management. We're not going to waste time on looking at the source. We're just going to look at the possible responses. When you are defining river management, that is a geographical concept which you can define according to your different dimension of understanding of the aspect of river management. But however, it must address the basics of river management. So we are looking at, when I talk of river management, we are referring to water resources and wetlands. The management of water resources, drainage basins, the wetlands, all those resources that facilitate us to get water for the benefit of sustainable clean water supply. That's our main purpose. We want to achieve sustainability for sustainable water supply, sustainable, clean, and safe water supply. That is basically water management, river management. We need to manage water sources, ways through which water resources can be managed, wetlands, drainage basins, for sustainable supply of clean and safe water for different uses. That is river management. Right. In which province is the eThekwini municipality? That is an extraction question, is in KZN. Our answer is here. According to the extract, what are the main causes of pollution from Umbilo River? Our main causes are indicated here. This is due to years of industrial pollution. So one cause, and inefficient sewage infrastructure, which results in raw sewage contaminating the water system. So those are the two causes: industrial pollution and inefficient sewage infrastructure, which is contributing towards. Right. Name one environmental impact of pollution highlighted in the extract. How did pollution impact on the natural environment? We are told that sensitive ecosystems along the path of Umbilo River system are also being destroyed. This is a natural, the destruction of the natural ecosystems. Right, in a paragraph of approximately 8 lines, suggest strategies that the eThekwini municipality can implement to protect the Umbilo River from untreated sewage. What can they do to limit the effect of untreated sewage in the river? Right, we can look at, I will try to highlight some of the aspects that we can use here. Right, protecting the river from sewage. What can be done? Right, we are told that there is ineffective sewage infrastructure. So we must address this. We must upgrade sewage infrastructure, because the poor infrastructure is contributing towards pollution of the river. Then what must we do? We must upgrade the sewage infrastructure. And also we must use legislation. Legislation here, we can start by enacting laws against sewer pollution in the rivers. The municipality will enact laws against the discharge and the disposal of sewage into the rivers. Then they also need to enforce the laws. It's not only about enacting the laws need also to be enforcement of the laws. They need to be enforcement of the laws to ensure that people abide by those legislations. And also, there must be awareness campaigns. Sometimes people do things out of lack of knowledge. Go to the communities and make them aware on the dangers of polluting the river. Using education as a tool can also be an effective measure. Educate the societies and the communities on the dangers of polluting the rivers, creating public awareness. And also encourage reporting of cases of pollution. If anyone is seen polluting, then the community must report such cases. Or if there's a leakage of sewage somewhere, which the municipality hasn't noted, they must be reported. So there must be effective reporting systems to ensure that the rivers are not contaminated. And also, we can look at our private-public partnerships. The municipality can partner with some other institutions and some other companies to try and find sufficient funding to ensure that there is a proper and a sustainable management of the rivers. Private-public partnerships in development. Partnering with other companies, private companies, who are willing to give a hand and sustain the river. Then we can also look at innovative technologies. We come out with new technologies of handling sewage. For example, in sewage treatment. Effective methods of sewage treatment which are modern, which will help us manage sewage and not have it contaminate the rivers. That can also be an effective measure that can be put into action. Right, so by the look of things, this takes us to the end of our theory section, which is our section A. Quickly, we move on to section B, which is a map work question. Our map is based on the Malelane area, and there is map information there. It's also crucial that you read the map information because it will assist you in answering some of the questions. You do not just need to ignore the map information. But for the sake of our discussion, we just leave it. Right. So taking it to our questions, in which province is Malelane located? We find that on map information. It's here. Malelane is a gateway to the Kruger National Park, Mozambique and Eswatini, formerly Swaziland. This charming farming town in Mpumalanga. That is where we find Malelane. Is in Mpumalanga province. So our response, Mpumalanga. The grid reference number located to the east of Malelane map 2531 BC. I'll quickly illustrate this for the sake of those ones who are not very aware of the grid referencing system. It's 2531, 25, let me look at the reference, 2531 BC. Let me write it so that I can use it, 2531 BC. Right, 2531 BC. Right, this, I'll just quickly explain what this letters represents. This represents 25 degrees latitude, and this represents 31 degrees longitude. And the bigger block subdivision, and this is our smaller block subdivision. Right, so I will make the illustration. We are saying our latitude line is 25 degrees, which means we have 25 degrees here. And our line of latitude goes like that. And when we're picking our coordinates, remember we pick our coordinates from the northwest corner, which means your referral longitude is 31, which means your 31 is coming here, and your line of longitude goes like that. So this is 25, 31 in this block. The bigger block that we have is having 25, 31, which means the next block, if we are to continue on our map, the next line of longitude, the major line of longitude is going to be 32 degrees. If we were to have the next major line of longitude, it was going to come somewhere here, and it's going to be 32 degrees to the east. Right, this is to the south, and this is going to be 26 degrees to the south. Our latitudes, they increase going towards the south. We're in the southern hemisphere. Our longitude are increasing towards the east. We are in the eastern hemisphere according to the prime meridian. Right, so what it means here is this is a mapped area. The mapped area is a big area which cannot fit on one map. So what we do bigger block subdivisions. We divide this block here into two for the map to fit on the size of maps that we use for geography. And we use the bigger block subdivision, which is A in that sequence of the alphabet B, and we have C, and we have D. Right. Then again, this area again is too big to be mapped on one piece of map. We do another subdivision to make 4 more in each of those. So we are subdividing our bigger blocks into smaller blocks. So if we look, the original bigger block A was this. The original C block was this. And the original B block was this, whereas the original D block was this. But now we have subdivided them into smaller subsections or sub-blocks. When we're naming this, we start naming them by the main letter. Then we also use the same alphabet. So this becomes A, this becomes A, B, this becomes A, C, this becomes A, D. This becomes B, A, this becomes B, B, this becomes B, C, and this is B, D. This is CA, this is CB, this is CC, this is CD. This is DA, this is DB, this is DC, and this is DD. So our referral block is 2531 BC. Where is 3521 BC? Our BC is here. This is our area which is mapped. That's our mapped area. And so we want to refer to the question and try to look at the direction which is being requested for us to find the map reference of that given map in that given mapped map direction according to our question. Our question is saying, give the map reference of a map which is located to the east. So we come to our map here. Where is our east? We understand to the left is our western side. And this is our east. So we want a map to the east. So our map reference is 2531 BD, according to our findings there. So our correct response is BD, which is on item number B. Right, moving on to the next question. What is the difference in height between the contour line at 7 and the spot height 8 on the orthophoto map? Right, we just go to the map and try to find out information from the map and extract what is relevant there. We want the difference between spot height, between contour lines at 7 and the spot height 8, right, on the orthophoto map. Right, our orthophoto map is here, our 8 is here, our 7 is there. Checking our values, 7 is the index contour line, this one here, and our value you can see is 300. It's written here. And for this spot height is here. Our height is also, though it's not very clear on this map that we have here, but our height is indicated here is 382. So our difference is 382. Remember, our heights are in meters, minus 300 meters, which gives us 82 meters. That's the calculation for that one. Right. Then the next question is saying, use the answer in question 331 to calculate the gradient from the contour line at 7 to spot height 8. Use map distance of 4.5. Right, we'll do the calculation. Already we have our, when you're looking at its VI, gradient, our formula, says gradient is equal to VI over HE. The VI, what we call the vertical interval, is the difference in height between the two given points. And our HE is the actual ground distance. So in this instance, what you must do, the height difference, we have already found it. Make sure that you don't use a negative figure. You must always use a positive figure. Subtract the smaller value from the bigger value to get a positive value when you're calculating your VI. So we are saying in this instance, our VI, it has been already calculated from the previous question. We got it as 82 meters. What is our HE? Our HE, we are told that the map distance, use a map distance of 4,5 centimeters, which implies that this area here, we don't need to measure. It was supposed to measure from this part to this part, but it has been measured for us along this line. We do not need to measure that. We just need to use the information which has been availed according to the calculation that has been done. So it's 4.5 centimeters. And we need to convert it to the actual ground distance in meters so that we have a fraction with meter value over meter value. What do? Our topographic, our orthophoto map, we are taking the orthophoto map. Our scale is 1:10,000. If you want to convert this to meters, just multiply your measurement times 100 meters. If you want to convert this scale of 1:10,000 to meters, you convert by multiplying by 100 meters. Whatever you measure, you multiply it by 100 meters, you get the actual ground distance from the topographic map. If you want to convert it to kilometers, you multiply your measured distance and multiply by 0.1 kilometers. So here we want to use the meter value. So we are saying it's 4.5 times 100 meters, which is going to give us 450 meters. So this is our HE, and this is our VI. So our fraction is VI over HE. We are now saying it's 82 meters over, therefore, 450 meters. And remember, we do not solve this to get a decimal. Our gradient must be expressed as a ratio. And our ratio must have a numerator equal to 1. So in other words, we are saying, how do we make 82 equal to 1? We divide 82 by 82. Our meter is going to cancel with the meter. What we have done here, we must also do it to the denominator, divide also this by 82. 82 divided by 82, it gives us 1. Over 450 by 82, it gives us 5.487. So this as a ratio, it means now is 1:5.487, which we can round off to 2 decimal places to give us 1:5.49, like that. That is our gradient. So we are saying our gradient is 1:5.49, according to the calculation that we have done there. Let's move on to the next question. At this gradient, will there be more infiltration or more runoff with the gradient of 1:5.49? 1:5.49. With the gradient interpretation, it means if the denominator is a smaller number, the area is steep. But if the denominator is a bigger number, the gradient is general. So here, the denominator is small, which means the area is very steep sloping. Even if you check on the map, you can interpret here with the sequence of the contour lines. The contour lines are very close to each other. This is a hilly area, which is very steep sloping. So the question is saying, will there be more infiltration or more runoff? There is going to be more runoff. Steep sloping areas are going to have more runoff. What is the motivation? The area is very steep. Rainwater will not get any allowance to filter into the ground. It means if a raindrop falls over a steep area like this is a raindrop. It cannot find time to filter here. It will just have to go down the slope. It is going to go to run off. There is no time for this raindrop to filter here. It can filter if the area is like this. It comes here, it settles. Then gradually, it can filter into groundwater. But here, there's no opportunity. It cannot have time to stay here. It just has to flow down the steep sloping area. So that's the motivation there. The area is too steep, and hence, there is no allowance for raindrops to filter into the ground surface. They can only filter if they have time to settle on the ground surface. They cannot settle there because the ground is steep. The only way to survive is to flow down the steep sloping area. Right, move on to the next question. A wind that blows at night from spot height 504, don't need to go to the map. As long as you have seen that it's a wind that blows at night, and automatically that is a valley situation, it's a katabatic wind. Identify the negative environmental impact that the wind identified in question, whatever, can have on the Leopard Creek Golf Estate. Right, let's look at the Golf Creek Estate. We are referring to topographical map and we are referring to block B3. Right, let's go to block B3. B3, our golf course is where? Golf course estate is here. It's written here. And our wind is said to be blowing from here going there, which is flowing down into the valley. The golf course is ultimately into the valley. So we are saying, how does the presence of the cold air in the valley, how does it impact on the environment in that golf estate? How does cold air impact on the environment in that golf estate? So what we can say there, it can contribute towards the drying of the turf. Remember, it will be excessively cold and the turf might not be resistant to excessively cold conditions. So the turf may dry. That is one possibility. Because of excessive cold conditions, you might find that the turf in the golf course may be made to dry because of the extremely cold conditions. Or it can cause stress because of excessively cold conditions. They might be ground stress for the grass in the golf course. The grass might be stressed and will get stunned, might not grow because of the excessive cold conditions. Excessively cold conditions might be unfavorable for the growth of the grass in the golf course, and it might have stunted growth for the purpose of the presence of excessively cold winter conditions. And also, it can cause uneven moisture distribution. The distribution of moisture can be uneven in that golf course because of the presence of the katabatic winds. Right. Refer to line FG in block B2 and B3 on the topographical map. Draw a cross-section along line F to G across Ungwenya River. Provide for the following labels on the cross-section in undercut and a slip-off. I'll just go to the map and draw those two. Right, we want to draw line F and G. If we check line F, we are having a meander there. And on the part of G, we are having from F to G, we are coming from the outer bank and going towards the inner bank of the cave. This is our meander part of the river. You can see it's meandering here. So our line is cutting from here. So if you are to draw our F here and our G here, it implies that F is coming from the outer bend, which is a steep sloping, and G is a gently sloping side. So our undercut comes this side, and our slip off goes to the side of G. This is the inner, this is the outer. So this must be steeper, and this must be gentle. There's deposition here, which creates a gentle slope, and there's erosion here, which creates a steep slope. Right, then you can indicate your discharge level. That's basically what you must draw for that particular question. Right, moving on to the next question. The next question is saying, give one physical reason why Leopard Creek Golf Course is located at point G rather than at point F. Why do we find this golf course on this part here? Why is it on this side of G, where we said it's a slip off, and not on this side? The reasons are obvious. We'll try to highlight some of the reasons there. Let me use my drawing board. Right, reasons for slip off location for the golf course. Why is located on the slip off side of the river, a meander, is one, because of general topography. The area is gently sloping. You cannot have a golf course over a steep sloping area flowing into the river. It's a dangerous location. So it's gently sloping, which facilitates development. Can easily develop, and also maintenance. You can easily maintain the golf course because it's over a gently sloping area, and also it's on a more stable ground. Remember, there's deposition on the side of G. If it was on the side of F, there's erosion there, which means the area is not stable. So it's more stable on this side. Why is it stable? Due to deposition. There is more deposits being added to that area, and hence it's a stable area. And then if you look at also that side, there's more land available. For golf course development and expansion. There's potential of expansion there. Why? Because the meander will shift towards the side of the undercut slope, while it's adding more land on the side of the slip-off slope. Those are some of the reasons that you can justify the presence of the golf course on the side of the slip-off instead of the side of the undercut slope. The next question is saying, identify the fluvial feature at H in block C2 on the topographic map. Let's go to the map. The feature in block C2 on the topographic map, feature H. Okay. If you look at our feature H here, you can see that the river is braiding. That's a braided stream. If you check our H here is here, you can see that there are some deposits here within the river channel. So this is a braid. The river is braided. Right. The next question is saying, the feature identified in question 3.2, 323 is commonly found in the dash of a river, where the river valley is a dash valley. Right, it's found in the middle course, and the river has got a U shape. Item 1 and item 3, which is correct response, is response B. Right, sorry, it's not response B, it's 2 and 3, which is response C. I'm matching the wrong things here. It's item number 2 and item number 3. They are matched at C. Item number C. Right. Then the next question says, What is the general direction of flow of Umgwenya River on the topographical map? What is the general direction of flow? Right, featuring here, there are some things that you must note if you want to figure out the direction of flow. You can check if there's a dam. Check the position of the dam wall in that river. Unfortunately, we don't have a dam here. Also check on the clues about height. Rivers flow from high-lying areas going to low-lying areas if there are clues of height. And also check the tributaries, how they join the major river. And also check the fluvial features along the rivers. They will tell you that this river is going into the middle course, into the lower course. If you see the river meandering, it suggests that it's going to the middle course. If you see the river widening, having braids, it shows that the river is going into the lower course. Having more floodplains, it shows that it's going into the lower course. If the river is still too small and still very straight, it shows that the river is still in the upper course. So if you check this river here, if you check here, it's more straight and it's still a smaller river. But as it gets here, it starts to wind. It starts meandering. It means it's now in the middle course and it's now wider. The valley is now a U-shaped valley. As it goes down, it keeps on widening. And that is one evidence that you can use. So this river is basically going in the northern direction. It's flowing towards the northern direction. Or basically, if you can check the start point and the end point, we can say it's going in the northeastern. That's basically the flow direction. Right. Then what can we substantiate with? Give evidence to support the answer. What pieces of evidence can we use to say that this river is going towards the northern direction? Tributaries. If you check, there is one major tributary here. This one is joining at an acute angle, facing towards the north. And also this one is acute angle, going in that direction. So one is acute angles of the tributaries. The tributaries join at acute angles facing the south, which means the river is going towards the north. And also, there is clue about the valley of the river. The river is narrow here, but the river valley is widening as we get here, which means it's going in that direction. Or also, if you check the nature of the fluvial features, we have a straighter course here, which suggests that we are still in the upper course. And here we are having meanders, showing that the river is getting into the middle course. So the river is going in that direction for those reasons. Or if there was also a dam, we can justify using the dam wall argument. Right. Then the GIS question. Is the dam in block A5 on the topographical map? Block A5 is here. We have a dam. This dam. Is it raster or vector data? Topographic maps, they present features in the form of vector data. They are presented either as polygon or area features, as line features, or as point features. It is only on the orthophoto map where we have pictures. So whenever we're talking about a feature which is found on a topographical map, it is vector data. Give a reason. The dam is presented as a polygon or as an area feature. We know that vector data presents geographical features as lines, polygons, and points. But in raster, we use the pixels and we use grids. So that dam is presented in polygon as an area feature. It's a vector. Then buffering, basically we are looking at demarcation. Putting a boundary around a geographical feature, that is buffering. Putting a demarcation or a boundary around a geographical feature, that is what we refer to as a buffering process. Identify the land use feature at J in block A form. Right, we are referring to a topographic map. Let's go to block A form. J here, this green shade along the river. You see there's a green shade along this whole river here. So our J is referring to this green shade. We go to our map or key. We can see this area, the green shade, is representing the woodland. So basically, we can safely conclude that this area here around the river is a woodland. It's a woodland. Right? Explain how they use the land use feature identified in question 332B is an example of buffering. Why is that woodland an example of a demarcation or a boundary? Or how does it function as a boundary between the river and the surrounding activities? Right, we can say the woodland is responsible for controlling erosion. It controls erosion. We know well that the river banks are most likely to be eroded, but because of the boundary that has been instituted, the tree roots from the woodland are going to bind the soil and act as a control measure to erosion. And also why? It protects water quality. We need to put a buffer to protect our water quality. Remember, we'll be talking about water management, river management. So how does it filters out sediments? Filters out sediments. Some sediments which are likely to go into the river and contaminate the river or silt the river as filtered by the woodlands or even pollutants. Some pollutants are trapped in the woodland and cannot get into the river. And also we use the for flood mitigation. The risk of flooding is avoided by that woodland there. It's acting as a buffer to prevent flooding from getting into the surrounding areas. It's a boundary demarcating the river from flooding into the nearby areas. And then also we can look at as a temperature regulation measure. Benefiting aquatic life because of the shade. The woodland provides a shade in the river, which will help regulate the temperatures of the waters in the river and ultimately which is going to benefit aquatic life. We are not going to have harm happening to the ecosystem in the river because it's being shaded by the woodland along the river. And as a result, it's protecting the interest of the aquatic life in the river from harm of higher temperatures, which are caused by excessive incoming heat from the sun. Right. So basically, that's the idea behind Geography paper 1 as you have written it, or as you are viewing it. That's the basic idea of our geography paper. We must just have to focus on some of those aspects without much challenge. And mainly, our focus area, you must be familiar with your content in attempting the content section, section A, which is made up of our climate and weather question and also your section, question number 2 in section A again, which is the geomorphology, which is the river systems, and then your geographical skills and techniques, which is your map work section. You must also be familiar with your map work skills and reading maps and also doing map calculations. Right, that takes us to the end of this presentation. I hope it is going to take you a long way in assisting you to prepare for your exams, which will come at the end of the year. Thank you. Your host in geography will meet in other discussions to follow. A blessed opportunity to meet you on this platform again in the discussion of preparatory examinations for Gauteng province, paper 1 geography. As usual, I'll take through the question paper and also try to highlight on the possible responses and also try to give some brief explanations as to the justification of why we are opting for those options as the correct responses. Right. It is common to our understanding that our paper, one is made up of 3 questions. And out of those 3 questions, we're supposed to answer them in 3 hours, and they have a total of 150 marks. Implying that section A is a theory section, which is made up of 2 questions. Our first question is based on climate and weather, where we focus on the study of different weather phenomenon, ranging from the mid-latitude cyclones to urban climates. Then question number 2 is a geomorphology question, and our geomorphology focus in grade 12, we're mainly focused on the study of rivers. So that's the other question with 6 marks each, question number 160 and question number 260. Then we go to the section, next section B, which is question number 3. Question number 3 has got 30 marks and is based on geographical skills and techniques, which is basically our map interpretation. Right. So that's the structure of the paper, and you're supposed to answer everything in 3 hours.